David Smith here with one more flipped classroom math video. 3 tips before we start. First, remember you can speed up or slow down the playback if that helps you. Second, you can turn on the captions and watch my words go by along the bottom of your screen. Lastly, you can stop the video at any point in time and catch up with your notes. Today's topic is optimization. And what we're going to do here is mathematically determining the maximum height, area, or volume for a situation. Now, this process is widely applicable to lots of areas in life. If you're running a company, you want to maximize your profit. Things like that. So let's take a look at a problem here that illustrates this principle. We have a farmer who has 40 meters of fencing. That's all they've got. And they want to build a garden that's next to a barn. What dimensions provide the maximum area? So I've made a diagram here. Here's the barn, and she's building a garden out from the barn, and she's a smart farmer. She wants to use the side of the barn as one wall of her garden and save on fencing and get more area to plant the vegetables that she's planning on planting. So here's our situation. Now, we have 40 meters of fencing. So we need to come up with some kind of an equation where we can write our numbers on here and then maximize our area. So this is perhaps the hardest step here, is to figure out how to use variables and numbers to represent the lengths of our 3 sides. So I want you to pause the video right now and think real hard about that. How might you use a variable like x on this diagram to represent what we've got? We've got 40 meters of fencing and we have some x. So go ahead and give that a shot. Okay, let's see how you did. Here's the thing to realize, that this rectangle has 2 sides that are equal and then these sides that are equal. But we don't need to use fencing for that one. So we have 2 sides that are the same and we have one side that's something else. So what I'm going to do is I'm going to say that side is x, which means this side is also x. Now think real hard. What's the length of that side going to be? This is where the 40 meters comes into play. Okay, this one is 40 minus 2x. Do you see that? Like we have a total of 40. We've used x here and x there. So this one's going to be 40 minus 2x. So now write an area equation for the garden, because that's what we're trying to maximize. Okay, pretty straightforward. The area of the garden is going to be x, this dimension, times 40 minus 2x, that dimension. Now we can expand this here, and we're going to get a quadratic. So here's what I got. I just did my distributive property, and I rearranged the equation a little bit. So x times minus 2x is minus 2x squared, and then x times 40 is just 40x. So that's the area of my garden. Now we want to maximize that. We want this area to be as big as possible. Now think for a minute about a quadratic. What are we trying to find with that function? Action. So what you have to realize is that this is going to make a parabola with a maximum. So we need to find the value of x so that that is the maximum of the function, or the vertex of the parabola. Remember, the parabola is going to look like this. And it's going to have a max. So we're going to have some function like that, where this is x and this is area. And area is going to increase as x gets bigger, but x gets to a certain point, the area is going to start decreasing again, because that's how a parabolic function works. So now, think real hard. How would you find that maximum? So the trick here is to realize that I can graph that function, and then I can use the trace function on the calculator to find the coordinates of the vertex. So what I want you to do now is pause the video, get out your fancy calculator, and do just that. Okay, I got into my calculator, I plotted this function, I used trace, and what I get is the max area happens when x is 10, and that gives us an area of 200. That's the biggest area we can get, 200 meters squared. How about this point? What would that point be? Now, at that point, at this x-intercept, our area is 0. So that means we don't have our rectangle anymore. And that makes sense, because as x gets closer and closer to 20, we're gonna be shrinking our rectangle down and down, so that if x is 20, there's no more width left. So we're just gonna have a line of double fencing with no area inside. So that's one example for how you can maximize a quantity using mathematics, using a parabolic function and your graphing calculator. So here is a problem that's definitely more complicated, and it's a good representation of the types of problems that you'll see on an IB exam. We're going to have to really dig deep to solve this one. Now also, maximizing is optimizing, minimizing is just a different way of optimizing. So what we're trying to do here is we're trying to find the minimum surface area of a cylinder with a volume of 500 cubic centimeters. And how this would apply would be, we need a cylinder to store this much volume. Say it's a water tank, and we want to store 500 cubic centimeters in that water tank. The surface area would represent the amount of metal that we needed to put into this project. And we want to minimize that because that's what costs us money. So we'd like to get 500 cubic centimeters, but we'd like to spend as little metal to get that done. So we want to minimize the surface area. So first step, I want you to dig deep and see if you can come up with the two equations that we're going to need to manipulate to solve this problem. Okay, the first one is volume. So the volume of a cylinder is pi r squared h. And what that really is just the area of the base times the height. That gets us the volume of the cylinder. Now, the second equation is the surface area of the cylinder. Now, pause the video, go look that up and see what you get. Okay, here is the second equation. The surface area of a cylinder is just twice the area of the bases. Pi r squared is the area of the base, and we have two of those. So it's twice pi r squared, and then it's 2 pi r h. And what that is the 2 pi r is the distance around, and then the h is the height. So what we've done is we've unreeled that curved surface, and we have 2 pi r is that distance, it's the distance around, and then h is the height of that rectangle. So in order to find a minimum, we need one equation. So what we're going to do here is we're going to solve the volume equation for h, and then we're going to put that in for h here. And don't worry, we're not going to know what r is, but that's going to be fine. And then 2 and pi are known quantities, so we didn't need to worry about those. So go ahead and rearrange this equation to solve for h. Okay, so here's my solution solving this equation for h. And what I did is I put in my 500 for volume, and then I divided through by pi r squared. So I get h equals 500 divided by pi r squared. So now what I need to do is I need to substitute this term in for h and then simplify this equation down so I have one equation so that I can maximize or minimize the surface area with a volume of 500. So give that a shot, see what you get. Okay, here's my substitution step. All I did is I took this term here, put it in for h in my surface area equation, and I get this equation. Now, if you haven't gone further already, simplify this as far as you can. Okay, here's what I get. I can cancel out my pi's here. I can cancel this r out and cancel the squared out. And then this is on the top of a fraction, so I multiply that straight across. So I wind up with 1,000 over r. So now this expression shows us surface area of our cylinder as a function of r. So what we need to do is find the r that creates the minimum surface area. And that will tell us how we have to build our cylinder. So check this out. This is a parabola. It's a quadratic equation, has a squared. So it's going to have some kind of curve like this. And then we're going to have our r here and our surface area there. Okay? Now the minimized point is right here. This point keeps us at the lowest surface area, and it helps us find the r for that. And you'll notice that we don't have an h in here. We got rid of h by substituting r in for h. So that allows us to make this problem more simple and make it solvable on our graphing display calculator. So now what I want you to do is go ahead and put this into your calculator, graph it, and then use the trace function to find the value of r that minimizes surface area. All right, let's see how you did. When I put this into my graph in my calculator, I get a graph that looks like this. And if I trace to the vertex here, the minimum, I get r is 4.3 and the surface area is 349. So that means that's the smallest surface area we can use to get to get the same volume, to get our 500 cubic centimeters for our problem here. All right, so to finish this problem up, if you are building this cylinder, what else do you need? You need one more number. Pause the video for a second and think about that. You're going to go out and make this thing. You know your radius of your bases is 4.3. What else do you need to know? If you came up with the height, you're right. We need to find the height of our cylinder. That way we know how to cut out the pieces and we're going to minimize our surface area. So how would you do that? Take a look at what we've got going here. It's all right there. Okay, we have an equation that solves for h. H is 500 divided by pi r squared. So all we do is we do a plug-in step for that. So here's my plug-in step. I have h equals 500 over pi times r, which is 4.3 squared. When I crunch those numbers, I get my height needs to be 8.61. So now I know that if I want to minimize the surface area, minimize the amount of metal I need to build my cylinder, I need a radius of 4.3 on the bases, and I need a height of 8.61. Now, if you wanted to double check this, you could just put this into the volume equation, put the h is 8.61, put that here, put 4.3 there, you crunch those numbers and you should get 500.
Now that you've watched the video, take a moment to write down any remaining questions so you can be sure you ask them in our next class. You can also watch the video again if you need to deepen your understanding. And if you enjoyed the video, please click like.